Welcome to Episode 9, Flu Bug. This is the public health version of 2 VAT flow, actually 3 VAT flow since we will be tracking people starting well, getting sick and then recovering. Instead of gallons, we will track the percent of people in a town hit by a flu bug. 99% of the town population begins in the well but susceptible group, the top account in our model. 1% begin in the sick and contagious group, our middle account. 0% begin in our recovered, immune and not contagious group. This is our bottom account. What is new in this episode? The mechanisms for moving susceptible people to sick, then moving them from sick to recovered and not infectious. People communicate a flu bug by contact. So to generate a step-by-step infection rate for the simulation, we multiply the current percent susceptible by the current percent sick for each step. This creates a raw exposure rate. To preserve the town population at 100%, each tiny fraction of a percent removed from susceptible must end up in sick. Here are the paths for the infection rate signal and thus the percent of people to move. First step in the path is a scalar that will allow us to turn the infectiousness of the bug up or down. We will start with it at ×1. Here is the path to remove people from susceptible. It gets a negative sign. Here is the path to add those same people to sick. It gets a positive sign. What about recovering? In the real world, each sick person is sick for a certain average number of days. One might write a program to bucket brigade people through a sick time delay line, and then after 3 days, delete a day's worth of them from the sick account and add them to the recovered account. In the spirit of high school algebra, let's see if we can abstract the main idea from the 3-day bucket brigade sick experience. If people are sick for 3 days, it may be good enough in a simple model to just move 1/3 of the sick people to recovered on any given day. From a public official's viewpoint, it doesn't matter which people. He or she may just want to predict lost productivity from local industries, the need to extend the school year and so on. Our dependency sentences. The rate at which people move from susceptible to sick is proportional to how often they bump into one another. High sick and moderate susceptible may produce the same current infection rate as moderate sick and high susceptible. The dependency sentence for getting well is that our recovery rate is always 33% of existing sick. Will the flu bug get everyone? Let's run the model and ask the question again. We have a 2 VAT flow style humping curve between 2 S-shaped curves. Susceptible drops while recovered grows. Recovery, of course, lags susceptible by about 3 days to account for people being sick. What about our dilemma? Will the bug get everyone? As the percent susceptible and sick both eventually drop, catching the last fraction of a percent of susceptible people looks less and less certain. Eventually other bugs go through the town and it may be impossible to tell who is sick from what. At 60 days there is still 5.7% or so susceptible and a sick person to infect them is hard to find. What changes if we double the effectiveness of contact? We have a much faster peaking epidemic and we catch a lot more of the people. But out at 60 days we still have some susceptible people left. 0.24%, not 5.7%. What if we cut the effectiveness of contact in half? We end up with a very high percent not caught by 60 days, about 40%. So effectiveness of contact is super important. Now that we have done 2 versions of 2 VAT flow, let's move on to motion problems. The heart of these models is a chain of 2 accounts, one converting acceleration to velocity and the second right behind it converting velocity to distance traveled. We will return to 2 VAT flow in episode 17 for watershed management. VAT1 will be a California Sierra winter snowpack, and VAT2 will be a flood control reservoir that catches and stores this huge amount of moisture during the spring melt. This 2-VAT flow system has an automatic controller that responds smoothly to heavy snow years followed by drought years to keep California alive. See you back for Episode 10. An Introduction to Motion in Scilab. Scilab is software buy-in for the world's community. Help them with dollars, publicity, and contribute code. TTS Voices copyrighted 2014 and licensed by LinguaTech, GmbH. Visit them at linguatech.de. Text and Graphics copyrighted 2019 by William Rhodes Design.